Today is October 26th. This is Saturday. It's 12 o'clock Daylight Pacific Savings Time, Pacific Daylight Savings Time. And we have Eric Dollard on the call. We have Haka says, Adrian Marsh from the UK. Eric Dollard is going to be sharing stuff about his most recent book. And so probably about a month ago, we released electromagnetic induction and its propagation, which is related to the work of Oliver Heaviside. And part one and part two have been out for quite a while. And recently we released number three, which completes basically the series of books. So the whole trilogy is available. And if you go to emediapress.com, you can find that as an ebook. Or if you have, if you want to go to Amazon, you can just search for Eric Dollard and Heaviside, and that will come up with those books. And eventually we'll make the paperback available where it's all three volumes within one paperback, just to have one collection. As far as the ebooks go, those will just stay as part one, two, and three. But there is a discount if you don't have any of those and you want to get all three ebooks. Recently, let's see, as far as any updates, so all the books and videos are available through emediapress.com. On Eric Dollard's website, EPD Labs is a nonprofit. It's 501c3 registered out of Nevada. I'm going to go to his website and I'll show that. Okay, so on ericpdollard.com/donate, this is where you can donate by PayPal. There's even a Bitcoin link, or if you send checks or money orders, those come to Spokane. I just endorse those and send them down to the bank in Nevada. And so EPD Laboratories, being a 501c3 nonprofit charitable corporation, donations are tax deductible, and the organization is completely funded by your donations. And so in some of the past interviews, I think the last one or two Zoom calls, you can find those on my YouTube channel. If you just go to YouTube, you type in my first and last name, Aaron Murakami, you'll be able to see some of these live Zoom calls. Roughly, they're 3 to 4 weeks apart. And the last two, there were quite a few different slideshows, and Haka says and Griffin and Justin had contributed quite a few pictures and some walkthroughs on a lot of the work going on down in Tonopah, so that you can see that the donations are actually going exactly where they're supposed to, and that's to help further the research. That's in, a lot of the different presentations at the conference, a lot of these books. Right now I'm considering doing the conference next year. It'll be the Energy Science and Technology Conference. We're going to be having information on that at emediapress.com/conference. So on this page, emediapress.com/conference, that'll redirect you right to this page. This still has last year's information up. There's also energyscienceconference.com, and the information will be there. I don't know when next year it's going to be. Typically, we had them the weekend right after the 4th of July. And so depends on what happens after the elections here in the States, because a lot of people are worried that there's going to be some chaos, but who knows what's going to be happening. But if everything kind of holds together, and if I can bring to completion a few new products that I've been working on to put into production, then that's going to, definitely be a yes. It'll probably be 5 days like it has, in the past, from a Wednesday to a Sunday. That's all kind of up in the air. And, we'll have a lot of the regulars, with hopefully Eric Dollard and Adrian and Griffin and Haka says. And so a lot of these guys are kind of in the, the Tesla, high voltage, high frequency, a lot of the presentations you've seen kind of continuing on that path. And then there's going to be, some other people. So anyway, it's up in the air. I'll be giving updates in Energy Times. That's probably the best place to get updates on what's happening and announcements about these kind of calls. So if you go to emediapress.com/energy times, that'll redirect you to the sign up page that'll pop up any moment. Right here and it's free to join. Just name, email, sign up, go click the confirmation link, and there's a bunch of free downloads you'll be able to get. And this is where pretty much all the announcements go first. Let's see. Let me see if I can unmute Eric here. You see the unmute request, Eric?
Yeah.
You got it? Okay. Are there any announcements that you want to make before kind of maybe giving an overview? Because when I gave an announcement for these calls, the last couple newsletters, I mentioned that one of the things you wanted to cover are those books, the Heaviside series, part 1, 2, and 3, because part 3 has been out for about a month. So anybody following your work, and specifically anybody who's been, studying those Heaviside books, this is a chance to ask you any questions or to explore any of that material deeper. And then after that, we can bring on Adrian to share some updates and everybody else.
So is that a question to me, or?
Yeah, are there any announcements or updates that you want to mention before we go into the books?
No, not right now.
Okay. Do you want to give kind of maybe a little synopsis of part 1, 2, and 3 and what you wanted to accomplish with those books? And then let's see if anybody has any questions. That's going to be, if we're going to see if there's any troublemakers who's going to be popping up. So
Yeah, that seems to be something new. I guess that's a good sign.
yeah, right.
Means that the proper people are being irritated into hysterical and what have you behavior. We should excite them even further and see if we can get them to self-emulate.
So I'll bring up the let me find the website here for the Heaviside books. Okay, so right there on emediapress.com at the top right is a products link or a product search, and you can search for, if you just put in Heaviside, HEAVISIDE, then you'll see the research results. And if you click on this one, this is where they're available, part 1, 2, 3, or the trilogy, where you can get all 3. Do you want to kind of just give a basic overview of these books and what they're about?
Yeah, it's these are not books for the beginner. The introduction would be the what I wrote in Lone Pine called the Common Language of Electrical Engineers. That's more beginner based and establishes the symbolisms and basic mathematics for what's found in the so-called Heaviside books. The problem that exists presently is the knowledge of electricity has basically completely unraveled, and there's nobody in the engineering world anymore that even has the faintest idea of what the relationships are or what have you. And the academic physics and mathematics crowd has filled in the void left by the knowledge of electricity and reintroduced all their gobbledygook and useless symbolisms and dimensions and all that. So the situation is basically beyond repair. The manifestation is the electrical grid is rapidly unraveling. The electrical products that are sold are built quite evidently with absolutely no knowledge of the electrical forces involved, and everything is fighting everything else. The harmonics are out of control. Massive quantities of parasitic oscillations are entering the power grid and what have you. So it's basically a disaster. And it's built up so much inertia, there's no fighting. It's just like everything else in human culture and society presently. It's all heading for a flaming oblivion. So that aside, what the Common Language for Electrical Engineers and then these following publications basically reestablishes all the theoretical principles of electricity on a very common sense level. There's no exotic mathematics or what have you. It's all basically high school algebra. People like to say my work is too mathematical. Well, actually, the mathematicians say that it's not mathematical enough. So who am I supposed to go along with? Definitely not the mathematicians. So this was a presentation that I gave, what was it, last year? I've lost track.
The heavy side one,
That was the year before last.
I think it might have been a year before last, because
Yeah.
last year was the Tesla's 4-quadrant presentation.
Okay, yeah, year before last.
Hmm.
So I kind of give a pretty good description there, along with the text that's in these books. So I used Heaviside's title of one of his first presentations in the form of a paper, which was entitled Electromagnetic Induction and Its Propagation. This was in England, and the academic powers to be immediately suppressed it and had any further entries by him prohibited. So that tells you something right there. So I kind of picked up where Heaviside left off, and then Heaviside's work, unfortunately, is also a gluttony of mathematics and a lot of the inane symbolisms and what have you of physics, and it's not really a place that you're going to learn a lot directly. So what I did is I translated that through the basic principles and symbolisms established by Arthur Kennelly and Charles Steinmetz, which is the very foundation of electrical engineering theory, and then expanded upon what Heaviside had started from, and then basically quantified all the various factors and elements and forces involved in the field of electrical engineering, which you will not find in any textbook whatsoever. So these books are unique in that all the vagueness and mysteries and incompletenesses and all those type of things have been dealt with. Oh, I'd say I've probably been working on this for about well over 30 years. So this is kind of the finale of my theoretical electrical engineering work. With regard to the basic principles, I'm still moving forward with the polyphase theory and what have you. But as far as the basic electricity goes, this is carries it from beginning to end, and things that you will not find in any textbook whatsoever, even though you would think that these would be simple things that would appear in any basic textbook. They appear nowhere because basically the knowledge of electricity has been very successfully occluded by physics and the Einsteiners and all that. And so I think that kind of wraps up.
Do you want to mention just a little bit about who Oliver Heaviside is and how he fits into the whole category of electrical engineering and why he's important?
Well, Heaviside was a maverick theoretical physicist and mathematician who got his start on a practical level of working in the telegraph systems when they first began. And then he was the only one that was able to successfully tackle the mathematics of the undersea telegraph cables going between the United States and England for the most part, even though other land masses were involved. That's where the terminals were at. And the physicists of the time had come up with some goofy type of mathematics, which they made into law that completely defied any analysis of the undersea cables and actually directed you to construct them in a manner that would worsen all the defects. Heaviside managed to tackle the mathematical problem and was very heavily attacked and suppressed because of that, because the academic physicists were quite endeared to their useless mathematical formulations and weren't going to allow anybody to change it. But the fact that, the necessities and, the commercial aspects involved in extending telegraph systems on a transcontinental basis was so important, eventually Heaviside prevailed. But ultimately, his work did not really provide anything of use for electrical engineers because it was way too over mathematical and the symbolisms were very undeveloped and they still clung to many of the erroneous concepts of physics. So this is where Arthur Kennelly and Charles Steinmetz came in. They managed to convert Heaviside's extremely overcomplicated mathematical formulations into basic, simple algebraic formulations that were then adaptable to practical electrical engineering. And the same thing with regard to Maxwell's equations, which are regarded, almost as a religious icon, but essentially in practice, not only are they essentially useless, but will direct you in a manner that the results will be absolutely incorrect. And because the Maxwell equations, so-called, are worshipped as idols, the textbooks and the classroom electrical and electronics education, which clings to those, flat out keeps repeating the wrong results that just simply don't apply in the practical electrical world. And this exists in the electrical utility system to this day. It still labors under misconceptions that that completely prevent any possibility from understanding what's going on. So these books are, as far as for the electrical engineer or the electrical worker in general that can understand simple basic algebra, which you should have learned your first year in high school if you were to become an electrician or electrical technician. It's all brought into clarity. You'll know exactly what volts and amps and all these things mean, which you'll never get off any instructional videos. You'll never get it out of any classroom, and you'll never get it out of any textbook because everything is all garbled up with physics gobbledygook.
Okay, and if anybody wants to explore the work of Oliver Heaviside, have access to his books, I think you can just go to archive.org, and they're pretty much all available as free downloads, free PDFs. You just go to archive.org and go into the book search and type his name in, and you'll see different editions of the different books, but they're all free PDFs. Okay, Eric Sparkman sending a unmute request.
Hi, Aaron. I was just wondering where to get, if possible, the first edition of Occult Ether Physics by William Line.
Amazon would be the only place that I would know to get those, unless you find that somebody uploaded a PDF. I know I've seen PDFs of his books. I don't know what edition, but in Amazon, I know there's multiple editions available.
Okay. I've been on the shadow libraries and I can only find second edition and on.
Okay. Well, I know his son is on Facebook. I can't remember his son's name, but if William's old Facebook page is still there, you might be able to contact his son and ask him.
All right. Thanks, Aaron.
Okay. Okay, Victor, I'm going to send you an unmute request and you can go ahead and ask that. It's still muted.
Can you hear me now?
Yep. Yeah,
Okay,
go ahead, Victor.
I was wondering if your book on versor algebra would allow one to do the math beyond three-phase? Because I've been noticing some people are working.
It's for any number of phases.
Okay.
The problem with the versor algebra book is getting anything digitized kind of left it a mess. So the first volume seemed to pretty much work out okay, but the second volume, no matter how hard it was tried to get the format is the artificial malevolence in the system refused and just kept jumbling it. So we gave up at that point.
Okay. I'm
But
still
the,
reading.
but in order to take it beyond three-phase, I gave an entire presentation on this not that many years back of developing it for any number of phases with the emphasis on, I believe, ultimately on three-phase, but then of the last two presentations I did the whole thing for four-phase, all the way through, from scratch, all the way up to the most generalized equations. So
Okay.
I forget what the,
Is it the multiple coordinate system talk you're talking about, or
no, it was,
so I can
I
pull
think
it up?
that one came with the heavy side presentation because both of them had musical endings. So the electromagnetic induction and its propagation presentation was, I think it was the Fortescue. It was titled the Fortescue system or something. I mean, if you have some way to look at your list of presentations.
Yeah, I'm bringing it up right now. Let me do a screen share real quick.
And
Well,
then
people,
the official textbook on the subject is by two authors, Wagner and Evans, and it's called Symmetrical Components. It's the mathematics is not very well developed, but it leans heavy towards the practical application, so that probably would be very helpful. That was the only publication that I could find a workable general equation to turn into my general theory of versor algebra.
Eric, can you
okay.
see the screen with the search results there? The Steinmetz Fortescue method of analysis, and then there's the method of symmetrical coordinates.
Yeah, the method of symmetrical coordinates applied to the solution of polyphase networks.
That's it. A sequel to the work of Charles Fortescue, I believe, would probably be a subtitle. Yep, that's it.
Okay. Could I ask a personal question for you?
Yeah.
I've been looking into like batteries and energy storage for my radio gear and stuff and lipos, but considering that like lipo battery chargers have to have a chip in them, I was wondering what, in your opinion, would be the best type of battery, lead acid or simple, something that a guy could charge if the grid does go down?
Well, if they're going to float, where they're basically kind of on a floating charge all the time and they're running equipment all the time, lead acid's really where it's at. As far as if you're going to charge something up and then you're going to be in a position where you're going to drain it all the way down and not float it, nickel cadmium.
All right.
As far as
Okay.
all this newer stuff goes, it just seems to add a lot of complications, and the lithium batteries are basically incendiary devices, and I won't allow any of those things around anything, anywhere. They should, they're no good. They're really a bad idea. And on a very basic level, that because we live in an idiocracy, these basic levels are no longer considered. So
Okay.
metallic lithium is like sodium or potassium. It's violently reacts, and flames out, and it's just not something that you want in your environment. It's a time bomb.
Right.
Well, the
Okay, thank
lithium,
you.
the lithium iron phosphates are basically non-flammable. They're the safe option, but they're still very expensive.
Yeah,
I just won't use the stuff. I mean,
I find the charger needs a
I've
chip.
been fine with lead acid batteries and nickel cadmium batteries my entire life, all the way back into childhood. And I don't see any reason to use anything else.
Thank you.
Okay, thanks, Victor. Let's see, anybody else have any questions? You can click the reactions button and raise your hand or post a message in the chat room, and we can get you unmuted. So Eric, from the last episode, after Griffin and everybody was gone, and then after that, Justin hung out, we did a call on that. Are there any other, is there anything else that happened at the shop down there since then that you want to report on?
No, it's basically, it's stalled out.
Mhm.
There is no longer adequate funds to continue this project. And as far as manpower goes, basically, most people say they don't have the time or flat out refuse to cooperate.
So,
So basically, until there's adequate funding, there's no further work that can be done on those projects. So right now, I'm strictly in the writing mode.
so,
Very much
okay,
in the writing mode.
so do you want to go, Pat? So I guess we can move on from the books at this point. And, but what, you know, just say it's that, you know, we have the ability to fund the next episode. What are the next couple things that need to be done down there? Like what's on the agenda?
Well, finishing the pole pair, which is the antenna, so to speak, that's next. So I couldn't get anybody to come here during this interval to do it. But that's next. Now, Connor will probably come out here. Basically, I needed him here in October because that's the only weather interval to do that, and he couldn't make it. But he'll come out here when, you know, in November, where the weather will not be suitable to do any of that work for a number of reasons, hazardous and tensioning the wire, you know, when there's big temperature changes and high winds. And so there's only two things that we can do is road repair, which is a big job because we got miles of roads out there and some of them are severely washed out, virtually completely impassable. The other thing is to start stripping equipment here for the parts that are needed to do further work. Assume as far as the signal project goes, there's not enough solar power in the shack right now. There have to be money for that. Another pole has to go up because there's no longer any mass space for any further antennas. And of course, an antenna is going to have to go up for whatever radio link leads out of there to get on the internet. We don't have that pole presently, but there's one laying behind some business here in Tonopah that I think if I wave $100 bill in their face, we can get the pole. And it's the right kind. The hole has to be chiseled out of the rock. This is not something you can do with a shovel. So that would be next with the shack. Getting a duplicate solar panel for the 12 volts. That's all. These are all the things that are necessary to get the Earth ionosphere signal on the internet. And then, of course, there's elements that have to be built and put in the racks, but I find it very difficult to get people to cooperate to build things the way they're supposed to be. Everybody's got their own idea, so that probably will be stalled. I'm at the situation now that that pretty much a lot of the further work is going to have to be done by hiring contractors, and that's very expensive. So I would say if this project is going to move forward in securing the mine and getting the seismographs hooked up, getting the phone line run into town and all these type of things, it has to be $100,000.
So we could probably at least do another episode. I mean, you know, 5,000 at the bottom end would be helpful. 10,000 would be very helpful at this time. If anybody is able to donate, ericpdollar.com/donate, and you can donate by PayPal or check or money order. And again, they are tax deductible donations, being a 501c3 nonprofit. Okay, so yeah, what,
One more thing, if weather permits,
mhm,
Griffin's going to try to get out here during the winter vacation. It's very difficult right now for Griffin because he's involved in all these college courses.
mhm,
So it's really got him swamped. Other than on the weekends, he presently is working on further establishing the generalized Tesla and Alexanderson system on a widespread level. So he is busy working on the equipment right now. It's essentially a confidential project, so I can't give any further details on it because of obvious reasons, like we just got a taste of at the beginning of this Zoom call.
mhm.
So all that stuff does is just make it so that no one's going to hear about anything. Because the fundamental formula in this social media stuff, for every person that likes you and advertises as such, is there's two more that hate your guts and are looking for a way to stab you in the back. And I would just assume put this in a top secret project on the other side of the fence and just clam up. That's where I'm at with this.
Well,
Because
you and I have a 12-year history of being attacked by everybody you can think of. Long time and character assassination videos and the whole 9 yards. And the outcome is always here we are, stronger, more progress and everything else. And they just blew away like dust in the wind and nobody even remembers them. And that's what's going to continue to happen with these people is they're all irrelevant. But I do want to say something.
but not totally. There has been incidences recently.
Yeah.
We're not talking. Griffin and I are not talking about it, but because some of these projects are,
Yeah.
Starting to really be significant in various ways.
Mhm.
Some serious trouble's been made behind the scenes.
Yeah, I'm aware of some of it.
Yeah.
I want to address what Declan said in the chat. Could we start a GoFundMe campaign to help fund some progress? I would say, yeah, I mean, we had some success with some of the Indiegogo campaigns in the past. I've never tried GoFundMe. I do like the idea of the crowdsourcing. If there's somebody who can help really drive the traffic outside of my relatively small, network, then I think it's a good idea. I can only promote it to so many people, but I don't really have access outside of my network other than, through the forums, my own social media stuff and newsletters. But if you or somebody can get a lot of outside traffic, I think it's worth putting up a GoFundMe page. And absolutely, I'm 1000% for it. Let's see. Okay, we can go on to see if anybody else has anything. If nobody has questions, we'll see if Haka has any updates. And I know Adrian has some updates on some tube experiments, I think, that he's been working on. Haka says, let's see, let me unmute you real quick.
Afternoon.
Okay.
Okay, so for my update, last month's been kind of busy with some engineering projects. What I had been working on since in the recent past was, well, once we had the Tonopah station online and we were able to first get the seismic or sorry, the ionospheric signals on there, I was kind of fascinated with the sound and the simple description that little popcorn crackling sound that you would hear through the speakers was actually global lightning activity, like that it was a global receiver listening to the entire planet. And it got me really interested in part of Steve McGreevy's work, which was with the WR3 and a lot of these VLF receivers. He's been making them for a long time, but the problem was the receivers he made didn't have very good filters on them. So what would happen is you could only use these receivers when they were half mile, a mile, a couple miles away from civilization. Basically, the power line noise would always be so strong that the only thing you could hear through the speakers was this angry burr, and maybe in the background you'll get a little bit of the pops and crackles and the actual ionosphere stuff. So what I kind of hinted on the last couple of calls was that I was working on an improved version of that. And I actually did get to the freaking finish line this time. I actually just have a product that's actually finished, calling it the HARP 1 for Hakas's active amplified ionospheric or radio astronomy project. So essentially, it's a handheld VLF receiver that has a bunch of extra filtering built in specifically for power line noise and basically local interference, so that while the old systems you would only get that giant angry hum, this has a combination. It was sort of designed from the bottom up to fix that, so that it could be used in the suburbs or the city or any other place and still give a decent signal. Of course, it's orders of magnitude worse than what you'll find in the actual station in Nevada, just because, you know, of course, a 1,700-foot antenna field is going to be way better than a little 1-foot handheld. But what's nice is it does actually work off in the city. I'm in one of the worst conditions possible, which made for the perfect testing ground. It has two specific filters on here. One is a high pass filter that's adjustable depending on how bad your condition is. The other one is a band pass filter for if things are really bad out where you're at. Let's see. If you're interested, it helps fund some of my work. It's hakasays.com. I got about a dozen of them online that I put together. If anybody's interested, it helps fund some of my stuff and helps get some of these other things forward. But yeah, it's been a fun trip. I'm glad to actually have something. I'm glad this won't be a complete drain on my my personal funds anymore. If you guys are interested, exploring the world of VLF and also listening to local electronics like cell phones and all the gangrene energy that Eric's often alluded to. So
one thing that needs to be pointed out, not that it'll make any difference, it's not VLF. VLF is
correct.
3,000 cycles to 30 kilocycles. This is ultra low frequency, which
ULF.
is 300 cycles to 3,000 cycles. But of course, everyone is going to continue to say VLF because, you know, parrots always talk in unison. But properly, it's ULF reception.
Correct. Properly, it's ULF. I will tend to use the other terminology just because if you live in a country, I tend to speak their language.
Well, that country might be one to avoid because the textbook definitions and the established international definitions for the frequency band of 300 cycles to 3,000 cycles a second is ultra low frequency. Just like you can't say that channel 56 on the old TV band is VHF, because it's not, it's UHF. And if people just want to perpetuate the misconceptions because it's convenient or that's what everybody else does, then what can you say? Because that's the direction that everything is going.
I agree with you, but I'm not going to put let's say if I spend my war fighting terminology, I'm not going to get very far.
Well, if you just call it what it is.
Yeah, it needs to
I'll
be
use
technically
ULF in the standard systems.
I mean,
It needs to be technically correct.
Insistent that you have to call it the wrong thing because everyone else calls it the wrong thing? Why don't you just call it ULF? Because that's what it is.
I can call it ULF. Also, I had one person ask what the frequency range for the filter in the general setup. It's roughly 800 cycles to 9 kilocycles.
Yeah, I got to take a call real quick. Adrian is unmuted. If you want to go ahead and go into your updates and you can finish up Haka says, I'll be back in.
I'm good. Thanks.
Okay.
I'll hand it off to you, Aaron. Adrian, sorry.
Adrian. Okay.
Thank you, Hakasis. Thank you, Aaron. Aaron, can I can I? Well, let me just see if I can share screen. Aaron, can I share screen? A reasonable amount of time this year for me has been taken about. I had a lab move and getting reset up and things like that. So now that I've gotten back to regular research, I'm going to give an update on where I've gotten with the GU5B work that I'm doing. There are lots of things going on there, but I'm going to focus in one particular area. For those that are not familiar with this project, this on the screen, this is a system that I've been using for the golden ratio discharge research work. I gave a very comprehensive presentation for this last year at ESTC. You can see the coil system on the left. It gives you an idea of the kind of coil being used and tuning apparatus. And the GU5B power oscillator is the unit on the right here. That's had an upgrade, improved the cooling, and that's a final complete system. That's a power oscillator. So the project that I want to talk about is an extension to the GU5B system, where we have a unit which is ultimately a power amplifier, which is a push-pull amplifier. So it would utilize a pair of GU5B tubes, and that would be driven by a master oscillator. So this is a project that Eric and I have been discussing for some time now, and I'll move on to giving an update on that. So this system generates, for those that haven't seen it before, this kind of discharge. It's known as the golden ratio discharge. I presented on it in detail last year. Eric Dollard has also done considerable work on this. So the system now, what will ultimately end up with a power amplifier, a push-pull GU5B power amplifier, it's gone through several different ideas and approaches, and Eric and I have communicated over some different things. But it seems to the simplest way now to come to the final amplifier is to have the GU5B push-pull amplifier. It might start as a single-ended amplifier, and that will be driven by, let's say, a ham radio linear amplifier. So, in other words, it needs to be driven in excess of between 100 and 500 watts. It needs on the input to get the full potential of the output for that. So rather than build everything from scratch, they've been working on using a typical ham radio linear power amplifier as a driver stage. And then that can, obviously, it would need to be modified. And it can be also then driven by the typical ham radio exciter that would be used to drive those kinds of things, along with various types of modulation and all of those things. So it makes a convenient way of being able to drive the final stage. Now, if we look at this system here, so this is the result of using a power oscillator. It's oscillating at what we use as the parallel mode. So it's the lower parallel mode, and this coil, which is running at 2.71 megacycles. So immediately we realize that 2.17 megacycles is outside a ham radio band. It's between the 160 meter and the 80 meter band. So we can't just use ordinary equipment. We can't just take something off the shelf like a linear power amplifier and utilize that to drive at the frequencies that we're interested in. In actual fact, the frequency for research, the frequency range which is best to use, I've discovered is between about 1 megacycle and about 4 megacycles. And since there's a wide range of coils that we're busy testing, we want to be able to tune relatively straightforwardly across that whole band. So that really bridges the from less than the 160 meter band to beyond the 80 meter band. So therefore, modifications will be needed. So if we move on to this is a Kenwood TL922 linear amplifier. It's nominally a 1 kilowatt output. It's based upon a pair of 3500Z tubes. So it's more than, and it's actually a very nice build. This I am a Kenwood ham radio believer. I have quite a lot of their equipment. It's very well constructed, and it's from that era where all the circuit diagrams are available. There are virtually no semiconductors. It's not driven by a computer. It is really simply an analog system, and everything can be modified. It's built with proper transformers. It doesn't use inverters. So it has it lends itself very well to modification. And I happen to have one of these that I wasn't using. I used my other one on the telluric transmission platform. But this one needed a new role. So it's not something, I'm not going to completely disassemble it and reinstall it into, for example, a rack, rebuild it into a new module. It may be used again as a linear amplifier. So I've been looking at modifications that one can make to it and still keep it in its current form. It lends itself both to be using directly on the bench, and it can be rack mounted as well. So it is the right size to fit into a standard 19-inch rack. So it's compatible with the way that Eric and I have been looking at this project. So having a look from above, so we just orientate ourselves. It's a pretty standard. It has two transformers, which we'll actually see from the bottom. There's a single 3500Z tube there. It has a position for 2. This normally runs 2 in parallel. And then it has a pi-L matching network on the inside and the outside. So this is a grounded grid implementation. So you feed the input comes from the exciter. It's driven through the system, and the output then goes through a matching network, which we can see many of the components here. It has a standard pi-L matching, so it has a tuning capacitor for the plate. Then obviously combined with a low-pass filter, and we'll come on to that in more detail in a moment. We'll just reorientate ourselves with how it looks. This is the underside. So there we can see that's the main inductor on the left bottom there, the coil inductor, which is for the output tuning. It's quite well rated. So the power output of the pi-L is considerably more than the 1 kilowatt. It could probably run to about 2.5 kilowatts. In the bottom left, we have the various pi matching networks for the input. At the top left is they're the mounting plates for the tubes. One of the tubes is already inserted, and then the 2 transformers. So the transformer at the top provides the high voltage. Nominally, this device runs at 3.5 kilovolts. The 3500Z is rated to 4 kilovolts, and each one is around about, let's say, in normal use, it would be rated at around about 750 watts. So between them, in parallel, they have a theoretical nominal output of 1.5 kilowatts. Eric also notes quite a few tricks that allow us to get quite a bit more efficiency out of these tubes. Then the transformer at the bottom right, provides the low voltage parts of the apparatus. So the various control circuits, relay circuits, safety circuits. So all in all, it's a ready constructed commercial equipment which lends itself to modification. So this is the close-up of the input pi matching network. Basically, it's all controlled by the front knobs, and you select in and out these various filters. So each of these essentially forms a band pass filter for each of the bands from 160 meters all the way up to the 10 meter. You can also see in the top picture there's a couple of the high voltage shunt capacitors that are used in the pi matching network on the output. So we'll obviously need to make some modifications here at the input. I'll just let Eric's having a good look, so I'll just let him finish before I move to the next picture. So this is a close-up of the output. Now we have these capacitors around here. They're all high voltage, rated to about 5 kilovolts. And they are used as the various shunt capacitors in the pi output. This is the second inductor, and the first inductor obviously is more powerful and is much smaller. It deals with the higher bands. This, you would have that switched in series with this completely, would give you the 160 meter, the bands. Okay, so this is the circuit diagram, the Kenwood circuit diagram. Obviously, I'm just going to point out the important parts here. So on the bottom left there, we're dealing with the power supply. We're dealing with we've got the transformers on the left. We're dealing with the high voltage, which is basically a split plus minus pair off of a single single tap secondary. That splits it into positive, B plus, and B minus, which is then fed directly to the tube via some suppression chokes. The top right area is the area we're going to concern ourselves with today. So we can see there the two tubes. Top left, they're mounted in parallel, as is very common with this linear amplifier arrangement. This section here, this is the input pi matching. So again, these selectors select the bands, 160 meter, 80, 40, 20, and so on. And then we have the output matching at the top right here. We're going to concern ourselves mainly with that network, because that network lends itself very well to what we want to do in terms of not only matching this stage, the driver stage, to the final GU5B stage, but we might even actually use this as the final output matching. Because if we consider what we have here, let me move on to a close-up. Okay, so there's a close-up at the top right. We can see the arrangement. It's a very straightforward arrangement. So here again, we have the input pi. These are just bandpass filters, which are basically making sure that the signal come in matches the ham radio bands. We have the pi L matching at the output. Again, this is L4 and L5 combined with the various shunt capacitors that we see at the bottom here. And obviously the two variable capacitors. One is the plate. VC1 is the plate resonant capacitor. So in other words, to make sure we keep the plate as a real resistance at the frequency that we're operating. And obviously we have the load variable capacitor as well. So in other words, being able to tune that low pass filter optimally to whatever load it is that we're driving. We have the two tubes here connected in parallel. We see the input comes and they feed capacitively fed into the cathode. These are grounded grid arrangements, and the whole amplifier properly tuned has a gain of about 10 dB. So if you put 100 watts in, nominally you get 100 kilowatts out into a match load, and it really does actually deliver that. So I tried putting it into a match load, a 50 ohm match load at 100 watts, and it does drive a kilowatt into that match load. Now, obviously, as Eric and I have looked at the project, there's a number of ways of approaching this final stage. Ultimately, the best and most efficient, which is also Eric has the most experience of, is the push-pull. So the push-pull arrangement is where you have one of the GU5B is amplifying on the positive cycle, on the positive half cycle of the signal, and one of the GU5B amplifiers tubes is amplifying on the negative half cycle. So therefore, we are getting the optimum efficiency from our amplifier. Each half cycle is being amplified in the process. Whereas in this scenario here, we have two in parallel. So in other words, we are limiting the swing of our output, because ultimately with a 3.5 kilovolt plate supply, we can't really swing much more than plus or minus that. That's why, for example, the primary coupling capacitor from the tubes onto the filter, that's rated at 15 kilovolts. So the tube being a transconductance device, we are going to pull the current up and down, and the voltage is going to swing either side, up and down, either side of that plate supply. Now, if we were going to drive a push-pull arrangement from this, we have a number of possible scenarios. So our scenario could be, we use this in parallel, we drive it through its matching, and then we couple that through a transformer to the push-pull of the two tubes. That's going to be a pretty large transformer on the output. I mean, we're going to push quite a lot of power to get those GU5Bs really pushing. So we end up with something like a 500-watt coupling transformer at 1 to 4 megacycles is going to be quite a big transformer. Or we can think about splitting it before, so we can split each of those internally. So in other words, we put the coupling transformer at the input to the two cathodes here. So we drop this network, this pi network at the beginning, we take that away. We put a coupling transformer at the input to the two, and then we drive that through a matching network from our exciter, which is probably a much better possibility. Eric might comment more after the presentation on that. So then we would split the output at the top here. It would come from the same plate supply. They would come from a suitable choke. And then each arm of one of these tubes would then drive the cathode of its respective GU5B. That's probably a more productive way of actually using this system, but it will require more modifications since this system is actually designed to run in parallel. So what I thought we might do to start with is we use this as a single-ended, and we first of all set the system up by driving the GU5B single-ended before we progress further, which then makes our job quite a bit more simple. Nonetheless, we might still use this output matching as the output matching for the final GU5B. After all, we've got to do the impedance transformation from the output of the GU5B amplifier onto the coil. And that's significant when we want to drive both the parallel modes and the series mode. So the series mode, as it's so called, has a very low impedance. So, for example, in the coil system that I'm using, we might be driving impedance of only a few tens of ohms at, say, 2.7 megacycles. Whereas if we drive a parallel mode, either the upper or lower, then we're going to be driving something in the region of a 10 to 15 kiloohms. So we've got a very wide range of matching problem to solve there. I'm not going to cover all of that in this call, but in another call, I'll go into more detail about the matching strategies that we can use for driving both parallel and series modes. Here, I want to look at what I've done so far in terms of the modifications that we're going to make to this system. So if we take this, so let's first of all have a look at how we're going to modify this this output bandpass filter that we have here. So this pi matching system. If we take out the important components, we can simplify it down to this. So this is an LT Spice model that's a Spice-based computer model of the important components that we just considered. So if I just run through this from left to right, we are using, so the 2,500 ohms, R1, 2,500 ohms. That represents the combined plate resistance when it's tuned of the two 3,500Zs in parallel. So when it's tuned at 4 kilovolts, it presents an output impedance, which is actually resistance, so it's a zero phase, of 2,500 ohms. That's coupled through a 1 nanofarad coupling capacitor, 15 kilovolt coupling capacitor. The reason we need that is because on this side we are looking at a DC 3.5 kilovolts. On the output we are looking for just the AC. We can't send that through to the output. So we have a coupling capacitor. Then we have some of the very small shunt capacitors with a transient bypass. So a 20 puff transient bypass. And then we get to our first adjustable. So this is our plate control. If I just go back and show you the front. So there's our plate control. So this is our plate control. This is our load control. Both of those represent two variable capacitors. So this is now VC1. So VC1 is a parallel capacitor, and it allows us to tune the reactance out of the tube So in effect, it is at resonance. So that is when we talk about setting up a linear tube amplifier. We would dip the grid or maximize the power, or however the process is that you use to tune up your ham radio final stage. That is primarily done by this adjustment, and you are tuning the plate at the frequency that you are operating. Now, these values here are based on real measurements, so they're not based upon the circuit diagram. So when I measured each of these components, these are what they actually work out to be. So VC1 is represented by VC1 plus its shunt capacitors. That is when the various bands. That varies between 320 picofarads and 470 picofarads. This is all at the 160 meter band. So I'm not considering the shunts, for example, that would be involved for some of the higher bands. We don't need those. They'll be cut out. So the most shunts are in at the low frequency because it needs the highest capacitance. Then we go through those inductors. Those were those two inductors that we saw. So L4 is the small one at the front. That's that first big spiral that we see. The capacitor that we see in the middle, that was the C1. That's our 15 kilovolt capacitor that takes the output directly off of the plate connection. So each of the plates will be connected across here, one from there to here, one to here by a very small quenching network through the capacitor onto the first inductor L4, which deals with the higher band. You can see that there are shunts coming off of this capacitor. So for example, if you're going to switch the 10 meter and the 20 meter band, you'll be taking your output directly off of this inductor, and the other inductor will be switched out, effectively shorted out of the system. This is L5. So L5 is the one that you need for the 160 and the 80 meter bands. And when these are actual measurements, they're not off the circuit diagram. So L4 is 2.9 microhenries, L5 is 19.7 microhenries. That then takes us on to VC2. So VC2 was our load knob on the front. That nominally allows us to adjust this low pass filter so it has basically optimum transfer to the final load. So this is for tuning. The pi network can be seen as tuning of the plate at this end, and then a low pass filter, which then allows us to optimally match to the load that we're driving. I've put a 50 ohm load here, which is nominal, but normally we would be driving an antenna with this, which will have a complex load. So it will have a real and a reactive part to it. Ultimately, at resonance, we aim for that to be as close to 50 ohms as we possibly can. Or then we have to use some kind of other matching, like an antenna tuner or something like that between the linear amplifier and the final antenna. But for the purposes here, we're going to use a 50 ohm load, which is the optimum system load for this pi network. The additional components that are important is L18, which is a 1 millihenry. It is basically the shunt discharge inductor for C34. So C34 is our coupling capacitor. If we didn't have that inductor and we didn't have a load, then now we would be simply effectively charging that capacitor through the load. And we'll also be discharging that capacitor through the load. And since that sits with a potential differential of around about 8 to 9 kilovolts on it, so on a high swing relative to zero, that could sit with 8 kilovolts on it, and we don't really want to expose 8 kilovolts out. And certainly we don't want to expose that across our load. So L18 is the shunt inductor, which basically allows us to charge and discharge C34 safely. And then we have a final transient bypass before we get to the load. So these are our most important components for the.
What you're showing is to convert the ham radio equipment to push-pull, of course, would just really be an absolute nightmare. Best to leave it that way and then just have your unbalanced to balanced transformer go to the tubes.
Do you think the transformer would need to be too big, Eric? I was concerned it might need to be a very big transformer.
It's not that bad, and the input to the GU5Bs in grounded grid is 50 ohm.
Yes.
So
Yes.
basically, if you could, because there's no transformation ratio, you can get away using ferrite cores.
Oh,
You
okay.
don't have a big air wound coil or all
If
that.
that would be that, if we could do that, that would make it a lot easier.
Yeah, so you would have basically three windings of the same number of turns and the same gauge, because all three windings would be 50 ohms.
Okay. Okay, good. Good. Okay. Well, that actually greatly simplifies our strategy.
Yeah.
If we don't have to
yeah.
split, if we don't have to split the linear amplifier at the input, then it
Right.
makes it, we can use the output.
Yeah. To split the ham radio linear amplifier, you'd be better off just starting from scratch.
Yeah, probably. Probably so.
So as long as it remains linear, you're not going to get too much of a problem of a one-sided wave. And then if you have a one-sided, like a half wave coming out, then one push-pull output tubes will be running a little hotter than the other.
Okay.
But because the amplifier,
that's okay.
Yeah, because the amplifier is linear and it's got a pretty stout tank circuit, you shouldn't have to worry about that.
Yeah.
But there always will be the tendency that one output tube is going to get pushed a little more than the other output tube, unless you go push-pull all the way through and have very high Q interstage tank circuits, which makes for, a full Navy-sized transmitter that stands 6 and 7 feet high.
Well, look, I mean, we will get there eventually, but but at the first step, no, I agree, Eric. I think that's a very good. This is the most efficient, I think, way of us.
In your new location, do you still have three-phase power?
I do indeed, yes.
Good. Yeah, because you don't want to be driving this with a single-phase power supply.
Sure, I will probably start. I will probably start initial tests with a single phase, and then we can turn it up as we go. But yes, for sure, I have a three-phase supply.
Yeah, you're talking about some serious power in a setup like this.
Absolutely. Well, I mean, we wouldn't be doing it if we weren't.
Right. We're talking about basically, the rule of thumb is the power output in any decent designed amplifier is 5 times the plate dissipation.
Yes, indeed.
And another rule of thumb is the RMS AC output of a transmitting tube is basically the plate voltage divided by 2.8.
Where's the 2.8 come from, Eric?
That is the square root of 2 times 2.
Square root of 2 times 2.
So,
yes,
so
it is. You're quite right. 1.4
if
times 2.
Yeah, if you got two limits, 0 volts and plate volts, right?
Yes.
Like, let's say, 1,000 volts, 0 to 1,000 volts, then when the tube goes to full, modulation of its electron beam, then you will have a peak-to-peak AC voltage across the tube of 1,000 volts.
Mm-hmm.
So the peak voltage is 500 volts.
Yes.
And the RMS voltage is roughly 70% of the 500 volts.
About 340 or so, 300, something like that. Okay.
The tank circuit does tend to jack that back up a bit, depending upon the Q of the tank circuit. There's strange interactions that go on between the tank circuit and the tube that are not generally understood, because the vacuum tube is a parametric device. In other words, it's a voltage dependent resistor, so to speak. It's a controlled resistance.
Mm-hmm.
So it's varying its resistance in the AC cycle, but because that's such a mathematical nightmare to deal with, that's usually just ignored, and the thing is just thought of, as an amplifier and not really a parametric device. But technically, it's a parametric device, and you can pretty much get away with not figuring on that in an amplifier. But when you start to get into oscillators, that can cause a lot of problems, particularly like in regenerative receivers and stuff like that.
Well, you can't control it easily in an oscillator. It's okay. All right, Aaron, if if we're back on track, then I'll go back to screen share and I'll continue.
Actually, we got a couple questions on the chat too, if you're interested.
Could I? Yes, I do want to answer them. Could I
Okay,
just
put a
move
pin in
through?
it.
Yeah, okay. If I could just move to the end of the presentation first, because there's still more to come. We're only halfway through yet.
Okay, just a second. So what I did was I removed all the security options to screen share and all that for participants.
Okay, good.
Because it doesn't let you selectively choose who can share a screen. So what I'm gonna try is make you a co-host and see if that
Okay.
automatically gives you permissions without me enabling it for participants.
And we can edit that little bit out of the video, huh?
Yeah. So I took a note. That was about an hour, 19 minutes or so.
Okay, good.
I'll,
But then,
yeah.
okay, good. Good.
Okay. So are you seeing yourself as a co-host, or did you see a
I'll go ahead and share. Can I just go ahead and share screen?
try it? Yeah. See if it'll do it without
It looks like it's allowing me.
okay.
Do you see my screen?
It is, yeah. Okay, so that's how we're gonna handle it from now on, is I'll just make
Okay.
you guys co-hosts, and then I'll leave all the permissions off. Okay, go for it.
I mean, presumably for future live calls, Aaron, you'll just do by registration, huh?
Yeah, minimum.
Yeah,
Yeah,
minimum.
I don't know if that'll start, people could use fake emails and whatever, but
Yeah, I guess.
or
I guess.
disposable emails, but we'll see.
Well,
Okay, sure.
ultimately, we're doing these things for the YouTube presentation that comes out of it.
That's correct.
So-
Yes. Yes. So
So-
it gets edited out anyway.
Yeah, so basically, if it becomes so problematic that, to open these things up to the public, we're just gonna get this flurry of dismalities, then we just have to stop doing that.
Well, also, Eric, the other thing we can do though is if we did get to there, we could just do this privately amongst us, record it, and it can still go to YouTube.
Well, that's another approach to what I'm saying. Yeah.
Yes, yeah, indeed.
Yeah.
We could just so either way, this material will still get to those people
Yeah.
that really need it.
Yeah,
And
that's
that
what's
are
important.
really interested.
Yeah, is to get this out, to the people that want to learn this kind of stuff, or at least, kind of get the visuals on what it's about.
I agree very much so.
But this looks
Okay.
like a solution to prevent anybody from, doing a screen share and doing a bunch of stupid stuff on the screen, because you, as a co-host, you're able to open up the screen sharing, and I still have the screen sharing disabled. So this works.
Okay.
Yeah.
Okay. All right, great. All right, well, I mean, moving forward. Thank you, Aaron. Thank you, Eric. I'll carry on with the rest and we can discuss more at the end of the presentation. Okay, so now we understand the key important parts that we have here for this linear amplifier. So let's go and have a look at how it performs. So this was actually measured. As I said before, these are not taken from the circuit diagram. This is how it actually looks when you measure it. So if we run those analyses, what we see, so basically I have told it to, let me just go back. If you're not familiar with LT Spice, what I have told it to do here is take a number of scans to step this VC1 from its minimum to its maximum, and then take various measurements across that. That way we can see its full range. So here we are looking at the ratio V out over V in, and V out over V in. We're looking at on the left axis here is the magnitude of the impedance, or the gain in effect. Actually, not the magnitude of impedance. Sorry, this is not an S11. It's an S21. This is the transfer gain that we are looking at, and its related phase. So the red curve is when the VC1 is set to its minimum. So that's the tuning knob is its minimum, and we see it hits a bandpass peak at 1.66 megacycles. So that's still very far. This is the unmodified, how it looks unmodified. So this is what it performs off the shelf. If you were to go and buy one of these off the shelf, this is how it performs. When we adjust that knob into the middle, then it hits 1.81 megacycles. So now we're at the bottom end of the 160 meter ammeter band. Then when we go to the wind it all the way to the top, Eric, just to recap, as you missed this bit, this is the transfer gain response of how it looks unmodified. So the red curve being the very minimum tuning at 1.66 megacycles, all the way up to the green, which is 2.1 megacycles at VC1 448 picofarads. So that is the full range of tuning of the off-the-shelf linear amplifier in the 160 meter band. So, well, that doesn't really help us in terms of what we want. I mean, I want to have a flexible tuning range of this amplifier between 1 megacycle and 4 megacycles, because there are lots of interesting points in between. So to make a change now we have a look at this circuit diagram again. What I've done is I've taken away L5 and I've put a variable inductor. So I put a roller variable inductor there that can be tuned between 0.1 microhenry and 53 microhenries. So in other words, it has one of these wind handles on the front, and as you turn it, I have a picture of it, I'll show you in a minute. You wind it and it has a little roller that moves along the inductor, and that basically changes. It's a very nice way to have a variable inductor. And in actual fact, this is the only component that we need to change. So now again, if we run the analysis with the minimum inductance that we need at 3.7 microhenries, I've indicated the important range here, and the maximum at 53 microhenries. If we run that again, so first of all, this is now we've set it to 3.7 microhenries, and our tuning now takes us all the way down to 1 megacycle. And if we introduce that tuning capacitor up to the maximum, it tunes us to 1.22 megacycle. But the main thing, this is the minimum position of the inductor, and we haven't lost any gain. So we are still operating nicely within the gain parameters, about 10 dB of the linear amplifier. If we now adjust that inductor all the way up to its maximum at 53 microhenries, now we're all the way up here. So now the green curve at maximum plate tuning capacitor is now 4 megacycles. And I can adjust that roller inductor anywhere in between. So in other words, I can move these curves anywhere, all the way from 1 megacycle all the way up to 4 megacycles, just by making that one simple modification. So by removing L5 or leaving it in position but disconnecting it and connecting a roller inductor in its place, I now can give myself that pi network is now flexible between 1 and 4 megacycles. So how does it look? Okay, so now I've turned the thing on its end, and my best way of being able to do this is to make a patch board. So in other words, I put a patch board on the side, which is compatible with mounting in a rack because it appears at the side of the rack, and this makes minimum distance connections to all of the various components. So in other words, I can plug in. I want to make it so that I can use it as it was, and also I can use it modified. So what I've done is I've arranged various jumpers here, which means that I can jump in the original inductor, or I can use an external inductor. And the white, yellow, and the blue, they allow me to switch in and out the input, so the input pi network. So in other words, on one position of the jumper, I could use the pi network on the input. So for example, this set of terminals basically goes, the yellow one goes to the input of the pi network at the input, and the other one goes to the output of the pi network. So by jumping the two yellow and white together with just a simple jumper, I connect in the existing commercial input filter. By connecting it to across the blue and the yellow, I now connect it to an external filter of my choice. So that might be a coupling transformer, it might be something else. So in other words, I turn the commercial ham unit into the flexible system, which I can switch backwards and forwards as I want to use it, just
You,
by a set of jumpers.
you might have a problem there.
Go on.
In that the inputs and outputs, they might cross couple to each other, and you will have an instability.
Possibly. We have to just try and see. I mean, the
Yeah.
frequencies are still relatively low.
Yeah,
I mean, when you look at the wire going inside, the amount of wire between one of these is no more than the internal wiring.
yeah. I just see there's a lot of capacitance between the high side and the low side. You might have. Is that panel metal or is it plastic?
No, that's a metal panel.
Well, you could make little cams that go over the plugs.
Yes, that's true. Definitely, that's true.
That would help
Yes,
a lot.
it could be shielded.
Yeah.
Good. That will be to bear in mind for testing for sure. Thank you, Eric. Okay, so this is how it looks from the other side. It's a relatively straightforward modification. And there's the roller inductor. So the roller inductor will basically be mounted on the top surface, so the whole thing can be mounted into a rack, or it can be used on the bench. It will have a wind wheel on the front, and then the output of this inductor will be wired directly into right where it's needed, into the side here of this unit. And
That's a
with
nice
this,
inductor. Where'd you find that?
I bought two of those about 8 years ago on eBay.
That's a beauty.
I've got two of those, Eric. So that's so we got a spare as well, you know.
Yeah.
But this is a nice one. This is all the way up to 54 microhenries. So this one component will allow us to tune our system over 1 megacycle all the way to 4 megacycles, which is the active interesting bands that I'm currently researching for the golden ratio discharge. If I were to play around with some of the other shunt capacitors, of course I can adjust that band to be bigger or to be smaller. But I want to try, if I can, to leave the rest of the internals of this system unmodified. It's all properly wired and balanced, and it runs very nicely. So I don't want to destroy it as a normal linear amplifier. So, well, there is in progress. I mean, it's not going to take too much work to finish this. It only has to have wiring, and then it's ready for testing. Okay, that is my last picture. That's the update so far. So, Eric, did you want to add anything? Do you see things? Any comments you want to make?
No, I mean, it looks good.
Work in progress. We're making some progress at last. So
It's moving along.
it's moving along. And also in the next live call, I will also look more at the matching between the final stage and the coil unit. So this will handle the matching between the driver and the GU5B unit, and then we will have an additional matching stage, and that one needs more consideration. And I want to bring out some of the design tools which are very useful in helping us to design that. So in other words, I will be able to take, like I do very much on my website and in presentations I've given in the past, I take S11 using a vector network analyzer, which is a real scan. It's a real scan of the impedance presented by the coil unit to the power amplifier. Then there are tools that are available which will take that and help you using Smith chart to actually do the proper matching of how that actually will look at the various points on using the real data. So therefore, one doesn't have to do a theoretical match based on, well, this frequency it's 50 ohms, at this frequency it's not. You can actually do a proper match. So I think they call it finite element matching. So it takes the real curve of the matching, and then it helps you to find the best network that you can use for maximum gain at the band and the center frequency that you want. So in our next call, I will go into that stage. I've already done quite a bit of work on that, so there'll be another update on that. I'll also probably have this, at some stage I will get this constructed, so then we'll actually take some real physical results, some real electrical measurements, and we'll see how it turns out.
You might be able to bypass all that. I've been quite successful in just with all the push-pull units I built of just the so-called primary coil, and the Tesla transformer is the tank circuit for the tubes.
The difficulty, I agree with you at the series mode, but the difficulty is the parallel mode. Because the parallel mode is such a high input impedance, because it's like 10 kilo-ohms, it's actually very difficult to make most tanks actually work with that. Well, that's what I've found anyway.
Yeah.
I mean, maybe you have a way of being able to do that.
Well, it's best to go by your experience, because I've never used the parallel mode. I've always used the series mode.
Okay, so it's good when we we can look at I mean, I agree with you. The series mode is relatively straightforward. I mean, we're only talking about difference of it generally down to a few ohms, even when you use, for example, particularly when you use like a swing link coupler or something like that. It's very easy to match. But the parallel mode, which gives the best, in my experience so far, the parallel mode gives the best golden ratio discharge. It would be good also to see that we can use the system to drive that mode as well, both upper and lower. Then we can do the full range.
The parallel mode is probably desirable for what you're doing because it's less likely to transmit.
Yes, indeed.
So, I mean, that's something you have to take into consideration. It's electromagnetic compatibility.
Of course.
Like you were talking about around 217 something kilocycles. Well, 2182 is the international maritime distress frequency.
Indeed.
So you don't want to be banging away on 2182.
Of course.
Or you might get a visit, that stuff is particularly tight in your neighborhood.
Indeed. Look, what I tend to do generally, I mean, my general approach to this, I mean, I know yours is similar, is that if you're going to run Tesla coils at the end of the day, it's impossible not to generate EMI. You are going to generate EMI if you run a Tesla coil, but we obviously need to minimize it. We need to put best practice in place. So using things like, for example, I do that by my lab is only in a rural industrial environment, so it's not close to other important things. It's out in the middle of nowhere, a bit like your kind of installation. You use a counterpoise. You use like a metal. You run the whole thing on a metal sheet in order to contain the displacement current coming off the coil. Use a counterpoise and then run it for short periods of time. I mean, no run of mine ever lasts for about more than a few minutes at a time, and that's happening. Maybe 1 or 2 times a week for running for about 5 or 10 minutes. So it's best practice to minimize, but I mean, you can't eliminate it. I mean, if you're going to run Tesla coils, you can't eliminate EMI. I would have said, unless you know of a good way, Eric.
Well, the push-pull, the balanced coil arrangement pretty much stops it from transmitting. What's that now?
I mean, even when we're doing these kind of like very special discharges and stuff like that.
Yeah, because one phase counteracts the other.
But it never really exactly cancels out, though, does it?
What's that now?
I mean, it never really exactly cancels out, huh?
Well, I mean, it's maybe 20 dB down or what have you, but that's still pretty substantial.
Yes, I agree. It is.
But at any rate, the experiments that you and I did pretty much indicated that the counterpoise really cuts back on that.
Yeah, it does. Yeah, I agree. It does.
So
and also the experiments that we did using everything on a virtual ground plane.
Yeah.
Because the virtual ground plane.
The other thing is because the discharge is short circuiting, for the lack of a better term, short circuiting the coil, that really inhibits its ability to transmit.
Yes, indeed.
Now, if you fired that thing up and managed to contain all that force without it bursting, forth into
Yes.
the air with the fiery blaze, you'd be lighting up the world around you.
Yes, indeed. Look, I mean, if we manage to contain that, I don't think there'll be much left of the amplifiers either.
Well, I mean, that's what we're doing here with the Tesla transmission stuff, is there is no discharge. So
Indeed.
So all that force is transmitted directly into the ground. But in order to do that, we either have to, use the frequencies that are available to me, as a ham radio licensee, or get permission from the Federal Communications Commission to transmit on specific frequencies.
Yes.
Yeah, Adrian,
Yes, indeed.
if you're able to stop your screen share, then when you're
Sure.
talking, we can have the full, I think it'll be the full screen. Yeah.
Thank you, Aaron. Yes, thank you. Yes, indeed. No, I agree, Eric. I mean, best practice in this work is it goes without saying. Well, in actual fact, it has to be reminded to a lot of people.
Yeah, you just don't want to make trouble for yourself. And then, there's so many idiots out there just blazing away, carefree with this stuff, and that could screw it up for everybody.
Yeah, indeed.
Somebody gets all tightened up over something and starts stirring a lot of shit, then all of a sudden it can just say, oh no, you can't do that anymore. And particularly in your neighborhood, it's really prone to that.
Yes.
I mean, I point out to people that, if I brought my car to your part of the world, the car would be immediately destroyed and I would be imprisoned for life.
Uh-huh.
That's why I live in America.
Indeed.
But it ain't going to get much better here. So,
well, that's the impression I get, but
yeah, it's not getting any better anywhere. But weather permitting, what we're going to try to do, notwithstanding getting any special FCC allocations or any of that right now, because that's kind of a long process, is we will go on the air with a couple 100 watts with the coil that Griffin built that's been well advertised on 1999 kilocycles under my call letters.
Okay, so in the one just right at the top end of the 160 meter band.
Yeah, so basically, the established legal situation is it's okay to operate between 1999 and 2000 with 100 watts in a so-called beacon mode, where you're transmitting without intending to be received, strictly for scientific purposes. And then, unless the weather turns on us, because December is not really a good time to do anything here.
Indeed.
The whole test platform might be buried in snow. But last time Hawkes manned the transmitter for a substantial period of time, and then we will advertise, and maybe this will be the beginning of the advertisement, is that will be the opportunity for people to try to tune in and see how well they can pick it up.
Yes. And the coil will be the Alexanderson?
Well, it'll be the Alexanderson shunt coil, scaled, yes. Okay. Scaled up to the ham band.
This is the one that's got the multiple pancake layers.
No, that's the Alexanderson shunt coil. That's the voltage coil. But the one that Griffin built, that's on the so-called 160 meter band.
I remember. Yes, it's a single spiral, isn't it?
Yeah, that's the one. For the Alexanderson antenna, the shunt coil goes between the overhead and the earth terminal, but the series coil goes in between the sections of the overhead. So the amps flow through the series coil, and the EMF is developed across the voltage coil.
So on the coil that you're currently using, what have you got on the top load? What is the top load?
It's an adjustable length of aluminum conductor, heavy gauge aluminum conductor.
Okay.
So we did, which is in the YouTube video, we did a very quick test up on an occupied portion of the 2 megacycle maritime band.
Yes.
Using maritime call letters. just for that one test. And that required an adjustable series capacitance between the output of the coil and the elevated capacity, which is an undesirable element because it's hard to weatherproof that and all that, because this thing has to sit out there no matter rain or shine or sleet or snow, dust and all the rest of that stuff. So I think when we go down to 1999, we can eliminate the series capacitor. It's possible to use strain insulators as capacitors because every insulator is a capacitor.
Yes.
And the nice thing about a strain insulator, is that when properly applied, one conductor wraps around the other with the dielectric.
This is the one with the two loops that interlock. Yes, I know those. Yes.
So it'll probably take a lot of futzing around to get it right, to get it down to that frequency. But but I think maybe we won't even need that at all if we just adjust the proportions of the elevated capacity.
And Eric, do you have the space there? I don't know how much space you have, but do you have the space there, for example, to set up a normal 160-meter half-wave dipole so you can compare the performance?
That would kind of strain our right-of-way lease agreement, but that lease agreement is flexible. We could do that out on our right-of-way.
Because it would be very interesting to do a comparison between your system.
No, that can't be done in town.
Okay, can't be done in town.
And we can't receive in town either due to all the immense gangrene energy that pours out of all the made in China apparatus that are in all the businesses around here. Right now, this pestilent gas station that's adjacent to the building is roughly putting a full kilowatt of microsecond transients back into the power line.
Oh, really?
That's how far out of control the situation's getting.
Okay.
It's horrific.
That makes it different. Yeah, it makes it that makes it impossible to almost do any reception.
Yeah, and then conversely, I have to be careful because, if it goes the other way and this multiple neutral thing that these idiotic power companies are adopting all over the world, I could burn out all the equipment in the gas station.
Yes.
So I can only, I can't do the 5 kilowatt station here because as much as I would like to incinerate all this stuff, I don't want to get punished for it.
It's called being between a rock and a hard place.
So there is another location that we can do that here. It would require to be negotiated, but the parties involved are up to that. There's an abandoned well on the water department land, and we did a lot of work for them for free. There's power there. There's enough a building that I can put one of the 5 kW AM transmitters on below the broadcast band and go full power with this as a Navy beacon. Of course, that would require a lot of money. Yes. But we do have all those possibilities here. It's just there's no money to do it. And like I say, I can't just do this stuff anymore with random, I'll help you if I feel like it, or I'm sick, or I got to work today, or what have you. We got to hire contractors, and that's all on a $100,000 basis. So we're stuck. But I try to move forward the best I can, which at this point is mostly writing. So I'm busy every day. I got those last 2 presentations are getting turned into books. Takes 2 years to do that.
Well, that's also important work, though.
Yeah, and boy, am I learning a lot. I'll tell you that.
That's the thing. When you have to write it down, you suddenly realize all the things you didn't know.
Well, yeah, right. Because how are you going to explain something to somebody that doesn't know anything about the subject?
Exactly.
Every sentence has to be worded properly so it doesn't have multiple meanings. I think, oh, well, I could do this with 3 or 4 drawings. Like right now, I'm writing the book on the Pythagorean coordinate system, which is something that I don't think anybody's ever talked about. And it's massive.
Yes.
I got into the preliminaries of it in my last music presentation at Aaron's conference. And then I started to use those drawings, and the 5 drawings that I started with now is up to 60.
You are having fun.
Oh, it's great. I mean, it's absolutely incredible. It's purely mathematical, but it
Uh-huh.
shows where the musical scale came from and why the musical
Uh-huh.
scale works and how
Uh-huh.
equal temperament came about, and all these major and minor scales and all these things that are all taken for granted. And to this day, no one can really give you an understandable answer. Why did equal temperament come about? Is it allude to, well, if you do this, it doesn't quite work right, or this, there's no, it's just like everything else in these endeavors, is everyone feels smug that, oh, well, we got the answer. Yeah, we know all that and what have you. But when they can't explain it because nobody really knows. They just
Indeed.
parrot the same stuff like this VLF thing. These people persist on VLF. It's not VLF, it's ULF. You see what
It
I'm
needs to,
getting at?
yeah, it
But
needs to be accurate.
but they won't move. You see what I mean? They'll continue
Uh-huh.
to parrot, they'll continue to parrot, and they won't move. What do you do in a situation like that when people refuse to educate themselves? Do you give up?
Yeah, no, you go and do something else. That's what I do. I go and do something else.
Brick
Well,
walls hurt your hand.
is I just get nastier.
Uh-huh.
Say,
And, if necessary, I have to get violent. That's the
You
only
don't want to do that,
appropriate
yeah.
response. It's called law
Just
enforcement.
go do something else which is much more valuable of your time.
Yeah, but you got to remember what I'm doing is I'm trying to steer this out of way, runaway locomotive back on the tracks before it smashes over the cliff.
Yeah, but you can't stand in front of the locomotive, Eric. That's not a good strategy.
No,
say,
but you can work on it from the side.
You can work on it from the side, I agree.
so we're, hey,
Or you could go further down the track and work on the track.
Exactly.
Sorry,
so we're
Eric, you
getting
want
on close to 2 hours here.
we're having fun.
We can probably cover a handful of these
Questions, sure.
questions.
If there are questions, yes, please.
And then I want to ask a question. Let's see. Okay.
Start one of them here is for Adrian. Is the GU5B system the one that produced the Dragon fractal?
Yes, correct. The GU5B, the Golden Dragon, which actually the Golden Dragon is a combination of, it's a fractal which is actually expanding at the golden ratio. So I showed it quite a few live calls ago, because I have a very good one that is the full Dragon expanding. I will bring it up again at the next live call because many people might not have seen it or been on that call. But that is, so what you get out of a Tesla coil properly set up, resonating at that right band of frequency and allowed to freely oscillate, and it is modulated at low frequency combined with high frequency resonation, is you basically get a fractal which expands at the golden ratio. If you want to see more details of that, I give a lot more detail of that in the presentation that I gave at ESTC last year. I did a full presentation on that. And it can be mathematically modeled. I mean, this is not it's not
Right.
something just arbitrary. If you take the fractal equation for a fractal, and then you expand that at the golden ratio expansion, you will end up with the same. I actually show the same mathematical overlay actually matches the shape of the discharge almost exactly.
So I think that was
I think
so if you can see my YouTube channel, February 17th, this bottom right thumbnail.
That's correct. Yes.
If you can
That is.
see that, that's
Can you make that bigger, Aaron?
Let's see.
Because that is the fully developed Golden Dragon. It's got the front legs, it's got the rear legs, it's got the expansion from both the front and the rear. It's properly defined in the S. The S is the full S there is basically what happens when you combine the fractal expansion with the golden ratio. Normally you just get half. I'll wait for it. Aaron, I'll wait to describe it till you can bring it on the screen.
Okay. Yeah, this thing won't cooperate. I'm trying to.
if
zoom
you
in
can't-
on it, and if I actually go to the video, it won't show the,
I can, if you give me a moment, whilst you try, I can pull up the original picture of it because it is an important question, actually. Let me look. I've got it somewhere here. It's not that one. It's the previous one, I think. Okay, I've got it, Aaron. I can
Okay.
share screen, and I've got the original image.
yeah, you should be able to.
Okay, thank you. Okay, that is the full Golden Dragon expansion. So it is the full S. So it's the upper section and it's the lower section. And that is when you take the fractal, the center point is here. When you take the fractal and you expand it by the golden ratio, you will get this upper section. And when you continue it into the, it's a complex number domain. So when you take it into negative complex domain, you get the bottom section as well. And this system was running, this was modulated, it was running at very high power. So I have a 5 kilowatt single phase supply. It's the maximum power you can pull out of I have 100 amp single phase supply at the place that I work. It's an industrial. I don't know if you have it in the US, but in the UK, you can have a single phase industrial supply up to 100 amps on a single phase. So I have a supply there, and that supplies a 5 kilowatt, a 10 kilovolt, 5 kilowatt power supply that actually forms the plate supply for the GU5B. And then this is actually running at full tilt, so 5 kilowatt. It's modulated. It's cathode modulated. I did show that at the time. And if you don't cathode modulate it, you can only get the upper section. When you cathode modulate it, you get the lower section as well. Why that is, I'm not quite sure. Eric, maybe you know why that is, but I don't know why it is. But normally, what you get looks something like. Well, let's take this one. You see, that's a lot of the top section. So there you have the top half, and there are lots of them all coming out. So that's a particular modulation frequency. You just get half of them; they're all coming out. If you adjust the modulation, this is still an area of research, then basically it starts extending out. It extends out further, and you get a top section, which is this section, and you get a bottom section as well. And in the most ideal case, it forms an S. So the fractal equation forms an S. If you look at a normal fractal, like the Mandelbrot or something like that, you will see that the mathematics define a natural S-curve. That is the S-curve, and the expansion of the golden ratio is based upon this curve here and where these tendrils actually break out. So where these tendrils break out is based on the golden ratio expansion. So that's why it's the golden dragon. The golden dragon is the combination of a fractal expanding at the golden ratio. And the GU5B push-pull amplifier that Eric and I are exploring and been discussing in this call is a more accurate way of being able to adjust the center frequency and the modulation. So this is all produced by a power oscillator. Now I have a pretty good power oscillator because that power oscillator is arranged to run at the parallel modes. So you can still get the golden dragon at the series mode, but it's not so well defined, or at least in my system, it's not so well defined. The parallel modes give a much greater definition. So what I mean by definition is if you look at the image that I showed today, look at the definition in that. That definition comes as a result. I've not seen that in the series mode. So in other words, the streamers are much straighter. They have less breakouts and they lack this fine detail. But the parallel modes give this extra detail. Whether or not that's a quirk about my system or the tuning, or whether that's truly about the parallel series mode, that's something that Erica and I are trying to explore. Because we conjectured basically that the parallel mode has more to do with the longitudinal, and the series mode has more to do with the transverse mode of energy, electricity transmission. Whether or not that conjecture is true is something that we're actually trying to explore. And we're using the golden ratio discharge and the GU5B amplifiers that we're building to try to test those conjectures. That's what we were also doing with the Colorado Springs experiment that we did last year at ESTC, and afterwards we did some additional work on that. I mean, Aaron has all of those. You can download all of those things. But that research is orientated to try to understand how all of those modes really work, how the dielectric induction and the magnetic induction fields relate. What is the relationship that they have? I mean, if you look at this kind of discharge, for example, I mean, this is not the kind of relationship between those two induction fields that you're going to see in Maxwell's equation. I mean, a dot or a cross product of those induction fields don't lead to this kind of discharge. There is a more complex, or even, should I say, a simpler. There is a simpler, more natural order relationship going on, which allows you to generate this kind of discharge. And that is the research. That is the research part that we are working on. And the whole point of building the push-pull GU5V amplifier is that it will allow us to control the parameters much more precisely. So the power oscillator has problems because if you move too far away from its center frequency, it becomes unstable. It's not so easy to switch frequency from. It's not easy to switch from the parallel to the series and back to the parallel without additional matching. So when we have this master controlled push-pull GU5V, the whole point of building that it is just for fun, but the fun has a real purpose in that it will assist us or allow us to make big strides with this research. So in other words, how do these discharges form? And what is the fundamental relationship between the induction fields that lead to this? Because this is a product of the natural order. I mean, what we are saying here is electricity demonstrates here specifically that is part of the natural order. It's not just something coming out of the wall socket. It's not just an electric field and a magnetic field as are defined in textbooks. There is a real life relationship here going on between those induction fields that lead to this kind of discharge, and also to other phenomena like ball lightning. Ball lightning, these kinds of discharges, the various like the root and the tree that Eric did so much work on when he was at Landers and stuff. These kinds of discharges and the work that we are doing, this fundamental research is demonstrating a natural order relationship between things that are just considered to be an electric field and a magnetic field. They don't have any relationship other than Maxwell's equations. But Maxwell's equations are only a relationship that describes a transverse electromagnetic wave in propagation. It doesn't speak of any other type of relationship between those induction fields. And clearly, when you get these kinds of discharges and things like ball lightning and other electrical phenomena, there is a relationship going on there, which is important to understand. And really, that's the purpose of what this aspect of the research that we're doing. It was good that question came up because it gives me a chance to put the reason why we're doing this in context.
Well, it's the same thing with the writing I'm doing is the existent Maxwell's equation religion doesn't tell us anything at all.
Yes, exactly. It's only one relationship for one specific thing, which was the transverse electromagnetic propagation.
Well, that's not totally true, but the thing is Maxwell died early in life, and he really was unable to complete his work. And at that time in history, the coordinate systems for this stuff were really not very well developed and very misleading. And unfortunately, they've been clung to. And what was fortunate about it is that Heaviside followed Maxwell, but only in terms of the transverse electromagnetics,
Yes,
but
indeed.
not beyond that. Now,
Maxwell did develop. Maxwell did develop the longitudinal. Huh?
well, there are those who say he did, but Maxwell's work is very primordial and it's not finished.
Uh-huh.
So, in a complementary sense to Maxwell, there's Helmholtz. So Helmholtz managed to develop a more broad rendition, but again, the mathematics and the coordinate systems were way overcomplicated and unworkable because he was using the same material as Maxwell. That's all there was at the time. And because that has been frozen into, you know, some kind of religious icon, there's no way to develop out of that.
Yes.
In the general sense.
Uh-huh.
I mean, people like me that, you know, point out, well, we got to go this way or go that way with it, are just simply ignored, or we get people drawing, you know, Greyhound bus station images on our discussion here. That's, you know, the best you get out of it. Now, there was a follower of Helmholtz that would be comparable to the follower of Maxwell, Heaviside, and that's Heinrich Hertz.
Uh-huh.
But Heinrich Hertz died at a very early age. So there's, even though by Tesla's account, Helmholtz was the route to go. And Heaviside was, you know, of course, in opposition to Helmholtz, which didn't help anything. We can't recover any of that material. It's lost. But it's good enough to know it exists and that Helmholtz and Tesla had collaborated on the Tesla system, which says something. And Tesla does talk frequently about Helmholtz in his writings and held Helmholtz in a very, very high regard. And he makes virtually no mention of Maxwell other than he called Maxwell the poet of electricity, but did not say what he meant by that. So that's kind of where we stand. Is this is all still wide open territory, just as it was in their time.
Oh, indeed, indeed. I mean, even our own research has only started to scratch the surface.
I mean, if there was adequate funding to do this on a purely, you know, laboratory level with all the necessary people and what have you, what could be developed would be absolutely fantastic.
Well, imagine what we could do if we had a Landers facility again and we lived in the same country.
Yeah, if everybody was here where this is supposed to be done, because it's protected here. This is the place to do it. I mean, after all, there's a 200 by 100 foot rectangle of absolute governmental fantasy land only 15 miles away from here.
Well, we hold out hope with the dream.
Yeah, well,
we have to.
As Walt, my friend Walt used to say when we built Landers, it all sounds great, but will I live to see it?
You are the eternal optimist, Eric.
Oh, yeah. I just go walk out the front door and look around me.
Sorry, Aaron.
So,
other questions?
Yeah, maybe get wrapped up here in a few.
Other questions?
Address, Eric Sparkman real quick. Yes, the Heaviside books are on Amazon. I showed us, did a screen share on that earlier. If you just go to Amazon and just type in Dollard and Heaviside, you'll see all three paperbacks available on there. And then let's see, one other quick question. Adrian, okay, was in the middle of moving shop. Have you had any more thoughts on the transatlantic transmission experiments?
That's at the moment. I did say in the last live call I was in that we did do some initial trials between Hackasys, Griffin, and myself. We were using very different systems. I have a good ground system. I mean, not as good as Eric's ground system, but I have a good ground system at my lab. and reasonably good. I mean, it's a 1,000 watts. It's a 1 kilowatt. It's a 1 kilowatt installation for telluric transmission tests. But we had very different systems matched from Griffin and Hackers's side and my side, so we didn't actually get a result in those initial trials. But now this project seems to have moved very much also with what Bruce Gavin is doing. I see he's on the call, so he might want to say something about it. But I know that he was designing coils, suitable coils, where, for example, I might have a set of those coils on this side of the Atlantic, and he has a set of coils on those side of the Atlantic, and we see what we can do between them. I know that he's busy in the process of that design. So I would say the future of that project at the moment is currently sitting with what Bruce is designing. Bruce, can you say some more about it?
Well, if you can hear me, can you hear me?
Yeah, I can hear you. Yes.
Okay, what are you seeing?
I'm seeing your
My mess.
workshop.
Okay. So I'm working through the phone. So here's I guess I can see it. Yeah, I can see
that's
it.
looking good. Yeah.
Okay, so this is a reasonable facsimile of the Tonopah beacon coil.
Okay.
It was built to the design that Griffin worked on, and I sort of interpreted between what the design said and what the reality was from the dimensions taken from the actual coil at Tonopah. So it has some, unfortunately, I had to design some deficiencies, in my opinion, into it to match the coil that sits at Tonopah. So, but anyway, the whole purpose for this is to finally see if at this scale we can get this primary to couple with the secondary, which has yet to be wound.
And what is that? 3 turns? Is that 3 turns on the primary?
Yeah.
Yeah. Okay. Yeah, I see that.
Yeah.
This is for the 160 meter band, Bruce.
Well, yeah, it's to try to. It's going to be wound up to match the frequency of the one in Tonopah, which I guess is around 2 megacycles.
Yeah, about 2 megacycles.
But I struggled with that because I wanted to cut the formers so that I could modify it and add turns and have a working prototype that had some functionality into it. And I think I've managed to do that. So everything's adjustable in terms of separation between the primary and secondary here. And it's even, thinking further out for getting on lower frequencies. I maybe could multiple stacks of these things. But we'll see how it works out. But so that some progress is being made, and within the next several weeks, I should have some results to report back to Eric and the rest of you guys. So that's about it.
Excellent. So when you've done the necessary research on this one, Bruce, and you've got it running up and running, are you going to make another one and send it to me?
Of course.
Right. then we can really, because then we will have a match system, and I know that you have a good setup there. You have a good ground, and you have a good space, and I've got that too. Then we can really see if we can actually do this, get this transatlantic telluric or other propagation mode, whatever the mode ends up to be. We see if we can get that working.
Well, I'm happy to share dimensions and things with you. It took quite a little work and quite a little money, but we'll see.
You want me to make it? You're not going to make one and send it to me?
Well, we can joke around all we want. Maybe something will materialize. I don't know. We'll see.
Well,
I wasn't joking. I was serious.
You could make the thing in kit form and send it to them.
Yeah.
Make it yeah. Form. It's all. You can break this thing down. These formers can be pulled out. They're slotted in place. I don't know.
Oh yeah. Look. If you make me a kit form, I can assemble that. Of course I can make that, but there are so many projects on the go. It'd be nice to have one. It would be nice if you make one and send me in a kit form.
Yeah, well, I can share my project list with you and we can see, when the, when the things will materialize. But no, I got a lot of things in the irons in the fire. But if I can get this, to show that a loosely coupled primary can excite, the secondary at a 50 ohm impedance, and it'll be useful to use traditional equipment.
Are you sure that's happening? You sure it's not just radiating off the primary?
Oh, I'm absolutely sure. Yeah, yeah.
So
It's the secondary is being fully excited with a very loose coupling in the series mode.
yeah, I was surprised that because you had quite a big gap between the secondary. I was surprised that you could actually get the power through it. Actually,
It
so I
loads
thought
up
maybe it was that. That's why I thought. But I can understand the impedance match for sure, because bring another coil like that in proximity, you will be able to adjust the impedance. So it's 50 ohms. But I was surprised that you could get the power.
Oh,
That's why I
the
wondered
power,
if it
the
was
power
radiating
can,
off the primary.
yeah, the power is equivalent to, I mean, if you were to series feed it and not
Yeah.
have a primary, or actually it's greater. The
Okay.
I've seen, maybe 18 to 20% more neutral current by feeding it with a primary as opposed to with a series fed.
Okay, it's very interesting.
Yeah. So anyway,
Very
we'll see. And I
Well, look,
gotta,
I mean, probably from your long list, you say you'll need to share your plans with me.
yeah. Okay.
Sounds like I'll need to make one of my own.
Right. Right. Well, we'll see how things go. Doing it a second time may be,
Easier.
certainly a little quicker, but I
Oh,
used
of
a lot of
course.
materials I had laying around here to do this, and the plastic, I had to purchase, but pretty much everything else was just laying around here.
Well, also, if you measure it and everything like that, you'll see simplifications, and the second one will obviously be simpler than the first one.
Could be, yeah.
But it always works out like that. The
Yeah,
first
of
one's
course.
always a struggle and it looks cockeyed.
Yeah,
The second one does it.
yeah. Okay, well, good, but that's a good. This answers this is where the transatlantic project is at, and it's good progress. It looks really good, Bruce.
Thank you.
So the struggle here, beyond the struggle of physically producing these things, is we have to figure out how to get a 90-degree distribution on the coil, which thus far has not been obtained.
Mm-hmm.
And that is going to take, both a mathematical and an experimental effort, because my theory is that unless we get that 90-degree transformation, it's not going to effectively transmit.
Does it have to be exactly 90
why we're not really getting any, wildly extraordinary response, propagation out of these things, is because that's a fundamental engineering requirement in any system like this. And particularly the Tesla system, is there has to be that 90-degree shift. And one of the big problems right now is that the potential null does not occur in the neutral lead to the ground, but it occurs in the coil, which Bruce has shown very clearly in his videos, that the neon lamp goes dark at some point on the coil, and then it's hot again going down into the ground, and that got to figure out a way to get around that. And there has to be exactly 90 degrees time shift between the current end of the coil and the potential end of the coil. And I believe if that's achieved, then all of a sudden the performance is going to skyrocket. I might be wrong, but that's just my gut feeling on the matter.
Have you achieved it before in the past, Eric, or is it still?
Well, I just haven't had the means to do that much experimentation on that level. So most of the coils that I have produced have been basically for the cosmic light bulb type stuff. So they're push-pull. Now, if they're push-pull, then you're pretty much going to get, you're going to get 90 degrees on either side of the coil because the thing's going to want to operate as a, unit, as a half-wave device. But one thing that's very important to take into consideration, and this is what I found in my experimentation out in Bolinas, you might have to have extraordinary insulation to handle the dielectric potential on the high end of the coil. But what's lacking is you have to have a very high degree of current carrying capability at the current end of the coil, not just a piece of wire. That's why in the connection to the underground tanks here, I do not use a single lead. It's a cage conductor. So in other words, it approximates a large cylinder. So you can't just run a wire from the neutral side of the coil to ground because the impedance is so low there and the current, effectively is so high that that lead just basically kills the oscillation and knocks it out of phase.
Hey, so somebody had a quick question here, if I can.
Yep.
Eric Sparkman, go ahead and
I had a question on a somewhat unrelated subject on the cosmic induction generator. I remember you guys put a tube in it, and you got a dark spot similar to a Crookes tube. Is that correct?
Yeah, a neutral plane.
What happens when you shine a laser through that?
Well, that's just pure speculation. I don't know. Try it.
I don't have one.
Build
All
one.
right, sorry, that's all I had.
Any other questions, Aaron?
let's see. I don't think so. Let's see. Let me scroll through the texts here. I think that was about it.
Well, it's not bad. It's a 2.5 hour.
Yeah.
So that's a good run at it.
Well, a lot of that was because of the interference.
Haka says, did you get your question answered about the output impedance of the GU5B? Was that covered?
That was my question. Yeah. It was Adrian. What is the natural output impedance of the GU5B amplifier you're working on?
You mean just the plate impedance?
The
You mean
ballpark
just the output of the
yeah.
tube? Well, the tube. Well, look, it's nominally 5 kilovolt anode potential, and it's a maximum plate current of about 1.5 amps. No, it's more than that. It's about 2.5 amps maximum. So
whatever ballpark that mats it into.
Yeah, what is that? What is 5,000 divided by 2.5? It's about
2,000.
1,600. Is that 2,000 or something? Yeah. So about 2 kilo ohms.
Gotcha.
Okay. We are on 2.5 hours here, so it's a long one. It'll take my laptop all night to render when I do this. But let's see. I can't think of any other announcements.
Just to ask, Aaron, do you know when we'll be having the next live call in about a month or so?
Yeah, let's see. 3. Yeah, towards the middle to the end of November.
Yeah. Okay.
Sometime. Yeah, I'll get together with Eric, see what works with him, and in the Signal chat, you guys can let me know what might work for you. But possibly the 16th or the 23rd.
Yeah, I was looking at those 2 dates as well. That probably would be good.
Okay, and then we'll find out from Griffin if he'll be available on those Saturdays, and if not, possibly a Sunday might work or something.
I think we're going to have to do Sunday because this project that Griffin's presently working on is of the highest priority, and we got to stick with it.
Okay, yeah, I'll get with Griffin, and he can let us know in the group chat what his availability is.
Some Sundays, Aaron, I won't be able to do, so we need to coordinate carefully.
Okay. Okay. I guess we'll just wrap it up then. An interesting call. Learned a few things on the Zoom, and I'll talk to a couple people about how to manage and prevent certain things
Oh.
from happening on the call.
Every one
So
of these calls is also an experiment.
yes, yeah, and I'm by no means a master Zoom moderator. So okay, so I'll put this video on YouTube. I'll subtitle it with some URLs. And again, as far as EPD Labs goes, it is a nonprofit. If you go to ericpdollard.com/donate, that's where you can help to support a lot of the efforts going on, at least down in Tonopah. That Hawkes has his own projects to kind of support some of his work with the
Well,
receiver.
I'll say if you have a side project or if you're interested in the low frequency reception and all that, then pick my stuff. But Eric's is more. I would rather you send some money to him because I'm self-funded. This funds some more side projects of mine.
And then Adrian has his website, am-innovations.com, and I think there's also a PayPal link on there. And then any of the books and videos from the conference, or anything outside of the conference, that's all on emediapress.com. Let's see, I want to share a quick YouTube video on my page real quick. It's just a recent interview I did. I get a lot of questions on all kinds of stuff, and this is primarily focused on the MWO, but I cover a lot of stuff. So the interview is kind of the world according to Aaron, but if anybody's interested, it goes into a lot of stuff that I'm always emailed about. So let me see. Let me share this screen real quick.
You're also considering me and Peter doing a walkthrough of some of those old Borderland videos.
Yes. So so if you can see the screen here with a few thumbnails, if you go to my YouTube channel, youtube.com, you can just type my first and last name and to the search bar, and you'll find my channel. You can subscribe to it. There's almost 450 videos, and but the most recent one you can see from 3 days ago, Lakofsky MWO Insider Secrets, Ether, Time and Space. I give my feedback on that, stories about meeting Eric and Bedini and Peter and all this, and how we even got into the MWO stuff. This Insider Secret stuff it's basically just going into some of the unbalanced things within Lakofsky's unit, the one phase grounded, the different number of turns on a secondary, and different lengths from the primary to the two different secondaries, because most people out there talking about the MWO just have these flea power little balanced units, and they're kind of radically different from what Lakofsky was actually doing. So I actually go into what makes an MWO according to what Lakofsky's manufactured units actually were. And I go into a lot of other stuff, but it's a little over 2 hours. And there's a good little slideshow of some stuff. I don't know if you can see that little Integratron picture there, but I tie different things in with the MWO according to my relationship with, Eric, Peter Lindemann, and Paul Babcock and all that. Over here to the right, this thumbnail, if you can see it, where it's got these old cosmic induction generator pictures in these bulbs, says Dollard Lindemann Part 1. So in June, towards the end of June, I set up a call with Eric and Peter Lindemann, so they could talk about some of the past history of borderlands and a lot of related experiments and people who they knew, and some of those kind of stories. Peter's been busy with some projects, but as soon as he's freed up, I'm going to set up another call, Zoom video call with Eric and Peter. And what I'd like to do is go through that video. I think it's called Free Energy Research, because it goes through, there's probably over a dozen different, motors and different technologies and contraptions and stuff, and different people are contributing to what these are, and, different demonstrations and stuff. Peter was there, Eric was there, possibly Michael Knox, and what's his name, Michael Thoreau, or if that's his name. But they're going through all the different explanations. And so it'd probably be a good idea to watch that video ahead of time. I'll post it on Eric's free video page. You know, it'll be on YouTube, but I'll post it in there in his page so that you can watch that video. And then it'll basically be commentary by Peter and Eric because they have the background inside scoop on a lot of those experiments and what they were trying to accomplish in that video. And I think that that'd be good to preserve, you know, get that preserved, and then possibly maybe do the same thing with some of the other Borderland videos. And that'll all be announced in the, you know, the newsletters, Energy Times, and, you know, on my Facebook page and whatever. So I guess with that, one thing I wanted to ask real quick is, so let's say we do a conference next year. I got to do some, you know, planning and thinking about the logistics and all that, and the actual, you know, date, you know, what might work for everybody. I got to take some surveys and stuff. But starting with you, Eric, if you're able to come up to the conference in person, or even if you don't, and it was streamed live from Tonopah or whatever it happens to be, what topic would you want to present on? Topic or topics?
Well, that takes a little thinking. So I won't be able to go because Griffin and I have this summer scheduled to concentrate on the electronics here, the amplifier project, all the modulators, and that kind of stuff. And that's really the only time that he has to engage. But I could do it kind of like we did with the Trump machine, you know, where I can send you drawings, and that worked out pretty good. And then somehow, you know, you got my image and voice out. That worked out okay. So I don't know. It takes, you know, I can't just think of anything at the top of my head. It's kind of maybe be, you know, what do people want? What do they want me to present? I could do it.
Yeah, and it may not necessarily be in the summer. I mean, that'd probably be the most convenient for most people. I mean, it could be in spring, it could be in September, whatever. So all that's up into the air, you know.
Well, spring is very good because being that, you know, I have to live, you know, in my car for an extensive period of time, you know, and travel through the valley of the shadow of death also to get to your place. The 4th of July is not the time to be doing this.
Okay.
May is the best.
Okay.
Because
what about you, Huck? Yeah.
Everything's still pretty green. People haven't, you know, started to flood the roads, and, you know, the fire hazards are not extreme, and May would really be good.
Okay. What about you, Huck says?
Timeline, I'm generally pretty flexible. We'll just have to see how that works. Topics, usually it's whatever, a combination of whatever I'm working on at the moment or per year, and some more esoteric, we'll say, philosophy of fringe science. So I don't have anything planned at the moment, but it'll be probably something mirroring pretty close to what was last time.
Mm-hmm. And a lot of times it's related.
I think Griffin might be okay with May too, but I'm not certain. Depends on his college program.
Right. Adrian?
My window for this really is, let's say, the latter part of May through to August. So that's the window. The autumn is not possible for me. I have other commitments. So yeah, that would be, if it was later in May, I think that would work for me as well.
Okay.
August is also a possibility for me.
Okay.
I don't know how that is for you, Eric, but
no, Griffin and I are going to be all summer. We're going to.
He got that program already.
This is going to be his Naval Training Center experience. And he's not going to want to miss it. And I need that kind of help. I got to have somebody here, you know, with his know-how and his ability that I don't have to supervise and, you know, fight with to get cooperation and all that. And we can get a lot of the electronics built here. It's just been lacking for years, particularly the amplifier project because of its commercial value.
Yes.
Okay.
And I would expect also, once Griffin is freed of this, this college curriculum, it won't be long before he has the first, not the first to be done, but the first existing presently seismic warning system. And he's in a good location for it. He's right on top of the San Gabriel Fault. So that's that basically has the highest priority of all the projects we're working on. And then a lot of the electronics we would be building here would be directly related to that project. So that's going to be a very important interval for us.
Okay, well, thanks all for joining the call. And yeah, I'll get this out on YouTube. We'll stay in touch, and we'll coordinate the next call towards the end of November. We'll just touch base in the signal chat and see what Griffin's got going on, and go from there.
Okay.
Great. Thank you, Aaron.
Okay, take care, everybody. See ya.
See you all later.
Okay.
Thank you.
Bye.
Bye-bye. Thanks, Eric. Bye-bye.